In section 7.2, we did two things. We found confidence intervals for population proportions, and then we found sample sizes to use when estimating sample proportions. In 7.3, we're doing the same two things for population means rather than proportions. In this section, we should know that the sample mean is the best point estimate of the population mean. That means when you're trying to estimate a population mean, you should use the sample mean as your very best estimate. Also, we will learn how to use sample data to construct a confidence interval for estimating the value of a population mean, and we should know how to interpret confidence intervals. And then last, we should develop the ability to determine the sample size necessary to estimate a population mean. Most often when we need to use a sample mean to estimate an unknown population mean, then the population standard deviation is unknown as well. Because we don't know the population standard deviation, we have to use a distribution which is wider than the normal distribution. We use a student t-distribution, also just known as a t-distribution. Student t-distribution is often referred to simply as a t-distribution. Because we don't know the value of the population standard deviation, we estimate it with a value of the sample standard deviation, but that's a little bit off. Remember in that formula for calculating sample size in last night's homework? If we knew the sample proportion, we used p hat and q hat. But if we didn't know the sample proportion, we had to go, we're going to have to play like it's 50-50 and let p hat be a half and q hat be a half. When you multiply those, you get a fourth. And that was what was in the other formula that you used when you don't know the sample proportion. When we used that 0.25 instead of our actual p hat, q hat, we had to survey more people, didn't we? Our sample size had to be bigger when we didn't know that sample proportion. Same thing here. The student t-distribution is a little bit wider because there's a little more error when you don't know the population standard deviation. In order to maintain a desired confidence level, such as 95%, we compensate for this unreliability by making the confidence interval wider. So when you don't know the population standard deviation, your confidence interval is going to be wider than when you do know the population standard deviation. We use critical values from a t-distribution that are larger than the critical values of a normal distribution to compensate for the fact that we don't know the population standard deviation. Important properties of the t-distribution. It's different for different sample sizers. Different sample sizers. Dadgummit, I did it again. Whew, I talk a lot in a day. The larger the sample size, the closer it gets to being just a normal distribution. If your sample size is big enough, remember, it doesn't matter if your population distribution is normal or not. But for small sample sizes, the t-distribution is wider than the z-distribution, and the smaller the sample size, the wider the t-distribution. Student t-distribution has the same general symmetric bell shape as the standard normal distribution, but it reflects a greater variability with wider distributions. That is expected with small samples. And the student t-distribution has a mean of t equals 0, just like the standard normal distribution has mean 0 and standard deviation of 1. the t-distribution has the mean being 0. You just call it t instead of z. All right. Same notation, mu for the population mean, x bar for the sample mean, n for the number of samples, s for the sample standard deviation. Sometimes you'll be told, hey, I'm giving you S. Sometimes you'll be told, hey, I'm giving you sigma. But most of the time, you're going to have to read the problem carefully to know whether you're being given S or sigma. To construct a confidence interval for the population mean, when sigma is unknown, use stat and test and t interval rather than z interval. When you pull up that screen, again, you're going to have to choose for input either data or statistics. If you have raw data stored in a list, you choose data. Make me a t interval based on this data that I have saved in list 1 or list 2. But if instead of raw data, I'm just given a sample mean and a sample standard deviation, make sure you have stats highlighted and just put in those statistics. All right, here's a problem. A common claim is that garlic lowers cholesterol levels. In a test of the effectiveness of garlic, 49 subjects were treated with doses of raw garlic. I don't know what happened to their cholesterol level, but I can imagine what happened to their love life. And their cholesterol levels were measured before and after the treatment. The changes in their levels of LDL cholesterol in milligrams per deciliter, have a mean of 0.4 and a standard deviation of 21. Hey, that's a pretty big standard deviation. There's some big time variance going on there. Use the sample statistics of a sample size of 49, the mean being 0.04, and the sample standard deviation being 21 to construct a 95% confidence interval estimate of the mean net change in LDL cholesterol after the garlic treatment. Now let me say something right here. If they had not given you this sentence or that phrase, the problem's harder. If they tell you exactly what to type on the calculator and you can't punch it on the calculator, I'm sorry for you. That's the easy part. The hard part was determining, it was easy to determine N was 49 and X bar was 0.4. But how do I know that 21 is the sample standard deviation rather than the population standard deviation? But I'm saying if they didn't tell you that was S, how would you know if that was S or sigma? That's a clue. That's a clue. Yeah, it tells you those are sample statistics. What if that wasn't there at all and it just said construct a 95% confidence interval?
Well, there's 49 subjects, and I can assume there's 49 people.
Yeah. But here's the key right here. That pronoun there is talking about the sample, not the population. The previous sentence said 49 subjects were treated and in their levels. That's referring to these 49, not everybody in the world or everybody in the U.S., whichever it is. So you have to see what the standard deviation refers to, and if it refers to the sample, then it's S. If it refers to the population, then it's sigma. But because we have the sample standard deviation, not the population standard deviation, that's why I'm going to use T interval instead of Z interval. Construct the confidence interval, stat and test, and number 8, T interval. we need to input the statistics. Sample mean is 0.4. Notice the symbol SX is used there for the sample standard deviation. Sample standard deviation is 21. Sample size is 49. And the confidence level is 95. I am 95% confident that the true population mean lies between what and what? Yep. What are the units there? What is the negative 5.6 and 6.4? This is, yes, this is levels of cholesterol measured in milligrams per deciliter. So these are milligrams per deciliter. The mean is between negative 5.6, and I'm sure that the homework will tell me what to round to. I just didn't think I had enough room there to keep 4 decimal places. Negative 5.6 and positive 6.4. Yes, ma'am. Go back to your T interval right here and let me look at see what you've typed in. You sure you have T interval instead of Z interval? You'll have to just go to it again, stat, and okay, you were in the right place. T interval stats. X wasn't it point? I think it was 0.4, and I put a circle around it, and you couldn't see it. Yep, 0.4. The rest of it's right. Tell me. Okay, that's a good question. Can you have a negative milligrams of LDL cholesterol in your blood? This is not just the milligrams per deciliter, or, yeah, that was right. This is not the amount. This is the change. Where does it say change? That's the change in cholesterol. Oh, so some folks' cholesterol went down 5.6 points, but some people's cholesterol actually went up 6.4 points. So this is not what their cholesterol level was. This is how much it had changed. We're 95% confident that the limits of negative 5.6 and 6.4 actually do contain the value of mu, but mu is the mean of the changes in cholesterol, which was said right here. The changes in their levels have a mean. It's not their level has a mean, but the changes in their level has a mean. Because the confidence interval limits contain the value of 0, zero's in there, what would the mean being 0 mean? It would mean no change. Negative is a decline, positive is an increase. If the mean was 0, then there would be no change. It wouldn't be standard normal, Sam, because not only would the mean have to be 0, but the standard deviation would have to be 1, and it's not. But if the mean was 0, that would mean absolutely no change. So it's very possible that the mean changes of LDL cholesterol is 0, which would suggest that the garlic treatment didn't affect the cholesterol level at all. As a matter of fact, for some people it raised it, for some people it lowered it, and for a lot of people in the middle it had no effect. If I were a myth buster, I would say this myth is busted. So stop eating garlic. All right, any questions? Example 2 is the same thing, except for we're given raw data. rather than being given the sample mean and the sample standard deviation. When we're given raw data, we have to put that data in list 1 or some list. And then when we go to t-interval, just choose data rather than stats. We need to construct a 99% confidence interval estimate of the mean length of all movies. Yes, yes. If I had 2 movies, say, that were 132 minutes long, actually I do. I could either put in 132 twice, or I can just put in 132 once and change its frequency to 2. It's easier just to leave it in, put it in twice. Where it depends on where. Oh, yeah. We couldn't change the frequency of just one movie right here. That would change the frequency of everything. So go ahead and enter the 132 twice. Make sure you have highlighted, choose the list, and specifically what list. I use list 1. You may have saved your data in some other list, in which case you'd need to change it. The frequency is 1. The confidence level is 0.99. And the t-interval is, that didn't help, 103.5 to 140. Is that what it says? 103.5 to 140. So based on this sample, we're 99% confident that the mean movie length, or most folks would just say average, but that's not a statistical word, average movie length lies between what? Yeah, minutes. This is 103.5 minutes and 140 minutes. Now, that's over a half hour spread. You know, the long movie is 37 minutes longer than the short movie, so that's a pretty big variation. If we knew the population standard deviation of all movies, then we could construct a z-interval rather than a t-interval, and we'd have a better estimate. We'd have a smaller range. We have a wide range because we didn't know the population standard deviation. Assuming it takes 30 minutes to empty a theater after a movie, clean it, allow time for the next audience to enter, and show previews, what is the minimum time that a theater manager should plan between start times of movies, assuming that this time will be sufficient for typical movies? How much time should be allowed between movies? Well, the average movie is going to last somewhere between 103.5 and 140 minutes. Which one of those ends of the range should you use if you don't want to take chances on running people out 30 minutes before the movie's over? You better use the upper one. All right? People are going to be mad and never come back if you chase them out 30 minutes before Lassie dies. I don't know if Lassie ever dies. You looked upset about that, Kelly. Lassie died? What? So use the 140 minutes and then add the 30 minutes to clean. You need to allow 170 minutes between the beginning of movies. Yeah, between start times. Because you have to publish the start times or put them on your little toll-free number or your Fandango, where you go to look up movie times, I don't know. You have to publish those start times way before the movie starts. You can't wait around to see how long the movie lasts and how fast the people get out. So most theaters allow about 170 minutes between their start times. What about Rocky Top 10? What have you noticed about their movie start times? They usually have a 4:30 show and a 7:30 show, or a 4 o'clock and a 7 o'clock. So they're allowing 3 hours. This is 2 hours and all of a sudden I couldn't do math in my head. Yeah, that's 2 hours and 50 minutes. So about 3 hours. Just to be safe that the movie will be over, everybody will be out, and we can clean up the popcorn before the next show starts. All right, the last thing we need to talk about this section is a formula for finding sample size for estimating a population mean. Just like in 7.2, we had two formulas for when the problem said find the sample size to estimate a population proportion. Here we're estimating a population mean instead of proportion. Our formula still begins n equals, because n is the variable that stands for sample size, and n equals z sub alpha over 2. We're going to find z sub alpha over 2 just like we did in 7.2 using inverse norm 1 minus alpha divided by 2 for a confidence level that we're given. We're also going to be given the population standard deviation and a margin of error. Z sub alpha over 2 times sigma divided by E, and then that whole quantity squared will give you sample size. Two important things: don't round your Z sub alpha over 2. If you do, sometimes you will get the correct answer, sometimes you'll get the incorrect answer. If you always want to get the right answer, then don't round your Z sub alpha over 2. And then also, like in 7.2, you always round sample size up to the next largest integer. Even if this formula gave you, for example, 80.01, if you only interview 80 people, then you won't have the desired confidence level. You always have to round up. So even if you just had 80.01, you would still round that sample size up to 81. Let's look at an example. Assume we want to estimate the mean IQ score for the population of statistics students. The population of IQ scores for statistics students has a standard deviation of 15 points. That said standard deviation for the population, so that is sigma. How many students must be randomly selected? The fact that it says how many tells me that I'm looking for one of my sample size formulas. And the fact that it says estimate that the sample mean is within 3 IQ points of the population mean means I need this formula from section 7.3 instead of 7.2. I'm not trying to estimate a population proportion. I'm trying to estimate a population mean, and this is the formula for sample size for estimating a population mean. If I want to use a 95% confidence level, that means alpha is 0.05. And my margin of error is 3 IQ points. Now in 7.2, this may have said 3 percentage points. If it was 3 percentage points, then we let E be 0.03, but this didn't say anything about percentage points, so E is just 3 IQ points. Substituting those values into the formula, inverse norm 1 minus 0.05 divided by 2 gives me this value. But if I don't want to round it or write it down and type it back into my calculator, I'm just going to continue with the formula. I'm going to not only find that inverse norm 1 minus 0.05 divided by 2, but I'm going to multiply that by 15 and divide 3 by 3. Notice that that whole expression had to be in parentheses. I had to open parentheses before I even opened inverse norm because I need to square that entire quantity. I'm going to enter that entire expression inside one big set of parentheses, and after I close that parentheses, then I will square that answer and hit equals. All right, let me show you what that's going to look like on the calculator. Z sub alpha over 2 for a 95% confidence level is inverse norm 1 minus alpha over 2, 0.05 divided by 2, close parentheses, close parentheses, multiply that by the standard deviation, which was 15, and divide that by the margin of error, which was 3, and I get that value to be 9.799. Now, I did something accidentally here, but it's fine. I forgot to open the parentheses before I started with inverse norm, and so I didn't close them at the end. This value is not my answer, but this is what I need to square. I went ahead and hit my equals button. Now if I square that, I get the sample size is 96 round it to 04. 96.04. But remember, sample size has to be rounded to the next highest whole number, regardless of what is in the tens place. If I want to be 95% confident, then I need to round my sample size to 97. And with a simple random sample of 97 statistic students, I can be 95% confident that the sample mean is within 3 IQ points of the true population mean. I want to re-enter this one more time. Since I didn't have the parentheses in like I had on my paper, I want to do it that way this time. The previous expression that I entered, since I forgot to open the parentheses, I went ahead and calculated everything that was inside the brackets in that formula and then squared it. And honestly, that may be the easiest way to enter that formula into the calculator. But if you do remember to open parentheses before you pull up inverse norm, then you can continue on 1 minus 0.05 divided by 2, close the inverse norm parenthesis, then say times 15 divided by 3, and close this very first parenthesis that you opened. And then square, and then enter, and you get the same 96.03, which rounds up to 97 statistic students. All right, so you have two formulas from 7.2 for constructing a sample size for estimating a population proportion. You only have one formula in 7.3 for estimating sample size for a population mean. Now you should be ready to do the next homework, assignment 14, and it's almost time for test 3, so make sure you do that practice test 3 before next class. Thank you.